This is the final 7.1 video. We're going to look at determining if a statistic is an unbiased estimator of a population parameter. So we've looked at sampling distributions of statistics. The two statistics that we've looked specifically at are sampling distribution of X bar and a sampling distribution of P hat. So an unbiased estimator is a statistic used for estimating a parameter if the mean of the sampling distribution is equal to the value of the parameter being estimated. So if the mean is equal to the parameter, then it's called an unbiased estimator. So we'll look at two examples here of an unbiased and a non-unbiased estimator. John and Carol have 4 grown sons. Their heights in inches are 71, 75, 72, and 68 inches. Calculate the mean of each sample and display the sampling distribution of the sample mean using a dot plot. So what we need to do is we need to create the sampling distribution. So we need to write out all possible samples from the population of 4 here. So it's a small population. And then write the means and create a dot plot to show the sampling distribution. So here I've listed out all possible samples of size 2, and I'm going to write their sample means here in the right column. I've listed out the sample means from each of the samples, and remember this is all possible samples. So I prepped a dot plot over here to plot these sample means, to write out to distribute the sampling distribution of X bar. So I'm going to plot 73 with an X bar above 73 here, and the same for the rest of these samples to create the sampling distribution. Here is the sampling distribution of X bar. And again, you can do dots and you don't have to do X bars. I just am reinforcing the fact that these are sample means. So if you look at this distribution, you can see that the mean of this distribution, or the balancing point, is going to be 71.5. And you could add all these up and divide by 6 and get that value, but you can also see it pretty clearly here that the mean of this distribution is 71.5, and I want you to get used to the notation that I'm going to write here. The mean of the sampling distribution of X bar is equal to 71.5. So to determine if this is an unbiased estimator, then the mean of this distribution will be equal to the population mean, because X bar is used to estimate a population mean. So we need to add these together and calculate the population mean. As you can see, the population mean is 71.5, which is equal to the mean of the sampling distribution. This means that X bar is an unbiased estimator of the population mean, because the mean of the sampling distribution is equal to the parameter of interest. Now let's do the same thing, but instead of creating the sampling distribution of X bar, we're going to calculate the range of each sample and display the sampling distribution of the sample range. So now we use these same samples, but instead of calculating X bar, we're going to calculate the range from each sample and plot those values. Remember, the range is the difference from the largest to the smallest. So 75 minus 71 will give us a range of 4, sample range of 4. And I'll do each of these for the remaining samples, and then I'll plot them on my dot plot over here. Here we have the sampling distribution of the sample ranges. So you can see this dot represents a sample of size 2 that had a range of 1. So that is this sample right here. Now, we can determine if sample range is an unbiased estimator if the mean of this distribution is equal to the parameter of interest. So if it's a sample range, that means we're estimating a population range. So the population range, if we look at the population, goes from 68 to 75. So that is a difference of 7. The population range is going to be 75 minus 68. So this is the parameter of interest, 7, and it's going to be an unbiased estimator if the mean of this distribution is equal to the population range. So we can add all these up and divide to get the mean of this distribution, which you can see is going to be somewhere about right here, this balancing point. And we would get a mean from this distribution of 3.67. As you can see, I added them together and got the mean of this distribution is 3.67, which means since 3.67 is not equal to the population parameter of 7, this is an unbiased estimator, which you'll see in a second is the next two questions here. Is the sample mean an unbiased estimator of the population mean? Explain your answer. Look up at the sampling distribution of X bar, the sample mean. Since the mean of the sampling distribution is equal to the population mean, the sample mean is an unbiased estimator. The next question is the sample range an unbiased estimator of the population range? Explain your answer. The answer is no, because the mean of the sampling distribution of the sample range is not equal to the population range. If they're unbiased estimators, then they would be equal. The last objective from this section is to describe the relationship between the sample size and the variability of a statistic. So let's take a look at an example problem here. To investigate the variability of a statistic, let's consider the proportion of people in a random sample who have ever watched the show Survivor. Survivor is one of the most watched television shows in the United States every week that it's aired. Suppose the true proportion of US adults who have ever seen Survivor is 0.377. So what that means is the population here is all of the United States, and the parameter of interest is proportion of people who watch Survivor during a week. So you can see there are two sampling distributions here, or simulated sampling distributions from this information. So for example, here is a dot at 0.25. This is a sample size of 100 people where 25% watched Survivor. And so we have, I don't know how many samples we have here, but we have a bunch of samples. You can see it is centered at the true population parameter. The true proportion of people who watch Survivor is 37%. So this distribution is centered at 37% because, as we saw, well, I guess we didn't see for p-hat, but p-hat is an unbiased estimator. The mean of this sampling distribution will be equal to the population proportion. But take a look at the difference here. This is the sample proportion who've watched Survivor from a sample size of 1,000. So the difference between these two distributions is the sample size here was 100, the sample size here was 1,000. And you can see that this distribution is much more spread out. There's a lot more sampling variability with the sample size of 100 than there is with a sample size of 1,000. So in conclusion, if we want to get a trustworthy estimate of an unknown population parameter, then we should start by using an unbiased estimator. But just because we're using an unbiased estimator, it doesn't mean or doesn't guarantee that the value of our statistic will be close to the actual parameter. For instance, based off of this sampling distribution, we got a range from 50% in a sample all the way down to, it looks like 22% in the sample. There's a lot of sampling variability because we have a small sample size, but when we increase our sample, we get more information, so we can be more precise. There will be less variation in our samples because now we have a sample size of 1,000. So you can see the range goes from 43% down to 32%. So there's a lot less variation. So in conclusion, you need to know larger random samples tend to produce estimates that are closer to the true population value. Basically, larger samples give you more info, give you better estimates. And what you need to know is larger samples means less variability in the sampling distribution of that statistic. But there is, just because you are more precise doesn't mean you're more accurate. You need to be aware of that. This concept here of taking a larger sample is only better if your sampling method is good. Because if you still have bias in your sampling method, then you might have less variability, but you may be still consistently missing the mark. So bias means that our sample statistics do not center on the population parameter, or our estimates are not accurate. For instance, this is not accurate because it's missing the mark, but there's not much variation here. Higher variability means that repeated samples do not give similar results. In other words, estimates are not precise. So here's a good picture of the difference between variability and bias. There's low variability here, but high bias because it's consistently missing the mark. Here we have high variability, but we have low bias because it's centered on the mark, but it still varies quite a bit. Here we have we have high bias and we have high variability. But this is what we're looking for. We want to have estimators that have no bias and they have low variability. So they don't change much and they consistently hit the mark over and over again. So bias comes from having the right sampling technique or sampling method, and variability comes from taking larger and larger samples. I'd like you to take a look and try these practice problems that will review from all of the concept 7.1.